Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm your host, Yoga Sri Pradhan, and with me here today, I have Kevin Wutherich from Drill Defract. I have the expert on me in this podcast, and today we are going to talk about URTEC 5628, which is covering the depletion, or let me go get the paper title real quick. It's called Improving Understanding of Depletion Around Fractures. I'm going to introduce Kevin a little bit before we start peppering him with questions. Kevin has 22 years of industry experience, both as an operator and in the service industry. Prior to joining Drill Defract as the Chief Technology Officer, where he has worked for the last 5 years, he was the Director of Completions at Rice Energy. Before that, he held multiple positions, including Stimulation Domain Expert for over a 15-year career at Schlumberger. Kevin pioneered the process of adapting completions to lateral rock properties over a decade ago and is the lead inventor on 7 patents related to fracturing procedures, perf techniques, and frac plugs. He's authored numerous SP papers and industry publications primarily focused on shale completions, as well as winning several industry awards, including the World Oil Award for Best New Completion Technology for his development of engineered diversion. In 2020, he was honored as a finalist for the Innovative Thinker Award, also by the World Oil magazine. Well, welcome to the podcast, Kevin.
Hey, thank you. I really appreciate you having me on here and looking forward to discussing some of this with you.
Of course. Well, before I wanted to talk specifics of the paper, I wanted to ask, what exactly does Drill Defract do?
Yeah, for sure. So Drill Defract, it's a company, we've been around now for about 7 years, and it's quite a long time. We started out really with the general idea of there's a lot of information in the drilling process that you can get. When you're drilling through rock, we can actually understand a little bit about what the rock's saying just by how the drill bit is acting. And the whole purpose of our company was really to take that information and be able to make actionable decisions on that, right? So, for example, what we really started on is looking at the strength of the rock, right? It just takes more energy to drill through rock with higher compressive strength than it does softer rock, for example. So that was sort of what we started out with. And since then, we've learned a lot more stuff. For example, being able to identify depletion. So that's really what we're all about. We're about getting that drilling data and then being able to make useful, actionable insights from that in order to better your completions, increase cluster efficiency, understand frac interactions, all of that. And it's all using data that you've already got. So, and we've been doing this now for about 7 years. We're a fairly small shop, actually. There's, I've heard some people think that they think that we're 30, 40, 50 people, but it's actually a really small group of professionals that are just dedicated to understanding that. So.
Awesome. Well, that's really good to hear. And I'm pretty excited about some of the stuff that y'all are doing. And when I was reading the paper, that's what really interested me on some of the things that were that you all are up to. And I had far more questions than the ones that I have listed right now. But for the interest of time and for viewers and listeners' attention spans, I think the questions I have will do. I wanted, in your terms, to walk through the URTEC paper 5628 to just give a briefing for those who haven't read the paper yet.
Okay, yeah, so this was a fantastic opportunity that we had from one of our clients. And, it starts off with our depletion mapping. And that's essentially, we started to figure out that as you're drilling a well, it just takes a little bit more energy to drill through areas of depletion. And when you understand everything around that and the context of everything, we can actually build a depletion map. And this is especially important when you're looking at infill wells, because what we're actually seeing is the fractures that cross that infill well and the depletion around it. So this paper talks about the first opportunity where one of our clients actually had image logs. So we were able to compare where we saw our depletion map with the imaged fractures. And that's exactly what we did. So we were able to learn about how do image fractures look in depleted areas versus undepleted areas. Another cool thing is that we had gas logs from the mud, and we got a really good correlation between what was happening with the mud gases combined with the depletion, combined with the image logs. So this paper was really an attempt to sort of bring it all together, help people understand sort of some of the mechanics around what's happening with depletion and how we can identify those.
Awesome. That's definitely been a hot button topic, especially when we're trying to figure out how do we complete some of our primary infill wells. And that ends up asking us the question, is it worth pumping more fluid, or is it worth pumping that much proppant in an area where we know that we're just not getting as much pressure contribution?
Mm-hmm. Yeah, and that's, you know, that's one of the interesting things about what we're doing here, right? Is because if you think about it, when we're seeing these pre-existing fractures and an infill well drills through it, that fracture, we know that it's connected to that parent wellbore, and it's connected to it right at the perforations, right? So if you start pumping into that pre-existing fracture, you're not breaking any new rock, right? The fluid's going to go right back into that original well. But not only will the fluid go right back into the original well, not break new rock, but we also think that that's one of the leading causes of why you get sand in that offset well, right? Because you're actually back flushing the original proppant right back into the sand, right? So, so that's one of the things that a lot of our clients have been seeing, is that if you can, you know, not necessarily change the volume that you're pumping or the amounts you're pumping or anything like that, but just making very slight changes and making sure that your new completion is not targeting those pre-existing fractures, you can do a pretty good job of actually preventing damage to your original offset legacy well, as well as, you know, making sure that the energy that you're pumping in is staying within that new well bore, just breaking more rock.
Yeah, of course.
Yeah.
I had a question about just understanding the areas of depletion and the types of fractures. What is that depth of investigation for fractures and investigating that depletion? Like, how far out are you looking at those fractures and that depletion?
Yeah, so I mean, we're just using drilling data, right? So when we're doing this, we're not running any tools down the hole, so we really don't have a depth of investigation per se. We're actually just looking at the rock that's being excavated by the drill bit, and so the depth of investigation is actually rather minimal. We can't see if a fracture ended, you know, 5 feet away from the wellbore. We can only see the ones that we're drilling through. But along those same lines, you know, besides just the depth of investigation, we can also sort of think about the time of investigation. And it's another thing to just realize with our technique, is that what we're giving you is a snapshot in time of when the well was drilled, right? So we see the, you know, if the parent well had been producing for 2 years, then you drill that infill well, we're getting a snapshot 2 years after that legacy well was drilled, right? So if you decide to complete that well 2 years later, we don't know what the depletion is at that point. So, you know, sort of the time of investigation is the time between when it was legacy well was put on production versus the infill well drilled. And depth of investigation, yeah, I mean, it's really just the wellbore.
Right, okay, that's good to know. Thanks for that clarification. In the paper, you talked about confidence rankings for identified fractures. And from your experience working with different clients, what's a quantifiable threshold for those confidence rankings? Because they seemed qualitative in the paper when I first read that.
Yeah, and that's one of the things. I mean, we do have, at this point, we are still trying to stay somewhat qualitative. The thing with using drilling data, of course, is that there's different levels of it, right? And with any type of measurement, there's always sort of that signal to noise ratio. if you have a lot of depletion and you've got just an average cleanliness of the drilling data, just sort of average drilling data, as long as there's a really strong depletion signature, we're going to be able to see that with fairly high confidence. What can happen sometimes, though, is if you're going through a process where there's some type of drilling, we call it drilling dysfunction, right? That might be that you're doing some steering events, or maybe there's some excessive bit wear, bit bounce, something like that going on. Problem is that drilling signal does get a little bit more noisy. Now, if we've got a huge depletion going through that, we can still see that and we can be very confident that that's what we're seeing. But many of the smaller anomalies, and when we talk small, we're talking about sort of in that 100 PSI of depletion, 150 PSI or less, then those ones we don't get as much confidence in, right? So we sort of just label those low confidence. We then label some high confidence. Those are the ones that we think are actionable, sort of like we're greater than 60 to 70% certain that these are caused by depletion, or very high confidence, which is sort of the 90 plus. And when we talk about confidence, one of the great things that we can do is we do this, what we call a context review. And that's sort of trying to look at all the depletion that's happening in context with all the other information we have. So good example is if you have wells next to each other, right? Two infill next to each other. If we can see a depletion event in one of them and also in the other one, but maybe we're not sure about one of those two, we can sort of look at between them. We can see if they look similar. Do they line up along the azimuth of maximum stress? Because that's the direction we'd expect fractures to go. And if there is some type of a correlation there, we can give it a little bit more confidence than we could with the well on its own. So we actually do quite a bit of work to try to, let our customers know how much confidence there is and how much confidence we have in it. We're very transparent about that.
Awesome. I'm really glad that you've mentioned some numbers for me, because I guess I'm a numbers person, and I want something objective to know what is high, what is low, and what's medium. I was also wondering, there was a bunch of image data. So I was wondering if you could discuss what had to be done to clean up that image data.
Yeah, so this is, I'm not an image log guy. I've seen a lot of image logs in the past, but I'm just not an image log guy. And my background's as a completion engineer, right? So as a completion engineer, I'm used to getting a lot of logs in, and you kind of take it as a ground truth, right? And so the first thing I did is when I got all this image log data together is I started putting it next to our data. And I noticed something really interesting, which is that every time there was a connection made during drilling, we were seeing a fracture being identified, right? And that was just puzzling to me. So I went back to some of our, some of the log interpretation guys, the people who work with that stuff every day. And yeah, they were explaining to me that these are sort of typical bit at rest features. Essentially, anytime the drill bit stops, to make a connection, you sort of finish drilling, they pull up the drill bit a little bit, and it might stay there for a minute or two as they're making their next connection, then they go down. Well, apparently, in many cases, what that does is it creates a little bit of a false signature. And if you don't give your log interpreters, your image log interpreters, that type of information, where those connections are, they may be falsely identifying those as imaged fractures, when really it's part of the drilling process. So that was one of the first things we had to do. We had to go and clean out all of those bit at rest features. And as it turned out, approximately 50% of the fractures that were identified by the log interpreter were actually effects from the drilling process itself, right? So, so it's just really important for us that maybe don't do this on an everyday basis, that when you're looking at that data, just be wary of that and, understand that these type things can happen. So yeah, we had to do a little bit of that ourselves.
Awesome. I'm sure, I'm not sure. Yeah, I'm sure that's pretty common as far as now that's part of the workflow, or that's part of the process.
Yeah. And I think the main thing that we learned out of this is that the image interpreter in that case, they're well aware that these things do happen, but they were not given the data from the operator that would allow them to sort of correct for that. So again, I think it's important for operators as well as anyone who is doing the interpretation to ask for these type of information, understand where those connections are. The other thing we saw is actually through sliding intervals. Every time there was a sliding interval, we saw sort of a dead spot in where they were measuring. So it's just important to keep a note on.
Awesome. In the paper, you talked about some common characteristics of fractures that have depletion that's associated with them. So what are they?
Yeah, so one of the first things I noticed, right, and of course what we wanted to do is there was a lot of fractures identified in the image log, but many, and actually the majority of them, did not have any depletion associated with them. Right. So the first thing we got to do is try to figure out, or one of the things we want to do with this paper is understand what common characteristics there are between fractures that are depleted in the image log versus ones that aren't. And one of the first things we saw is that it was about, I believe, 70% of the fractures that had depletion associated with them, we were seeing groups of fractures. So in the image log, we weren't seeing a single fracture, but we were actually seeing groups of anywhere from 2 to 4 or 5 fractures. And that was a little bit surprising to me, but I remember seeing that somewhere before. So I actually went back to some of the HFTS papers from HFTS 1, and they were seeing the exact same thing. And since then, I've heard a little bit more talk about it. And I guess, what people have called these now, or what people are calling them, are on echelon fractures. And so really what we were seeing is a lot of the depletion, the fractures that had depletion, were actually these on echelon fractures. So that was one of the things we saw. The other thing that we saw is that for the most part, when fractures had depletion associated with them, and let me back up, this was done with a resistivity image log, right? So it looks at the resistivity of the rock, and we can see those sort of changes, and the fractures show up as that difference in resistivity. So where we had depletion associated with the fractures, for the most part, we saw almost a little bit of a resistive halo around the fracture. So the fractures were sort of this black conductive line, but then you'd see this little halo of lighter colored shading around it, right? So a little bit of a resistive halo. In contrast, when we were looking at fractures that didn't have depletion associated with them, in this case, the fractures still looked conductive themselves. So we saw sort of a black line for the most part. But in this case, we saw this conductive halo around them. So almost a black smudge above and below the fractures. So when you put that in context with depletion, I guess one of the conclusions that I came to, or something that I believe might be happening here, is that when you don't have depletion, I believe that the fracture was created, a hydraulic fracture, but then the fluid leaks out into the formation. And that makes that surrounding rock a little bit more conductive, right? However, when you have depletion, what I believe is happening is now you're producing some of that hydrocarbon. We see that, well, what we believe in a lot of cases is that the lightest hydrocarbon comes in first. That's going to be the methane, ethane, all that sort of stuff is the first to be produced. And because of that, you actually get a little bit more of a resistive area around the fracture, right? So it's only one paper, only one look at it so far. Something we definitely want to explore a little bit more and see if that's something that, happens in more wells, but it's something that did seem quite interesting.
Awesome.
Yeah.
In the paper, how accurate is the depletion mapping technique in terms of the false positives and false negatives? I know that was mentioned in the paper.
Yeah. So one thing I didn't talk too much about so far is that we also had the ability to, or we had a really good mud gas log, and we don't always see this, but in this case, there was a really good correlation between what was happening in the mud gas in terms of the ratio of C1 to C2, C3, and 4 in total gas versus depletion. And what we saw is that wherever we saw depletion, we were seeing a decrease in the ratio of C1. That's just like what I was saying before, that we think it's because that's the one that's easiest to produce. So because of that, we have 3 different measurements. We've got our depletion mapping, we've got the gas ratio, and we've got the image log. So what we can now say is that if 2 of the 3 things are telling us the same thing, then we can essentially say that that's true. Obviously, if all 3 are saying the same thing, we know it's depletion. If 2 of the 3 are saying the same thing, we can sort of start to understand where the false positives and false negatives are, right? So using that type of a criteria, what we found is that our depletion mapping technique using the drilling data was roughly about 90% accurate in terms of both sort of false positive and false negatives. There were a few small anomalies that we did not pick up, right? So those would be sort of the false negatives. Of all of those, most of those, or really all of them, seem to be very, very small amount of depletion. In fact, looking back at the data, we did see a small little change in the data, but it was really within the noise. So all of the largest areas of depletion, it seemed like we were able to get. And there were 1 or 2 areas where we saw some depletion, again, relatively just above the noise, that didn't quite match up with anything else. So with all that, what we can say is that when there were large areas of depletion, significant depletion, 400 or 500 PSI plus, we had very, very good accuracy. In this case, it was looked to be pretty close to 100%. When you start looking down to the really low magnitude stuff, it drops down some from there. But on average, we're about a 90% accurate using our technique.
That's pretty promising. And so there's multiple sources of data that you're doing in order to confirm whether if it's a false positive or a false negative. Okay.
Yeah, we definitely try to incorporate all the data that we have, everything that's available. Of course, we can do it without all that data. And the important thing is that really all that ancillary data, all it does is help change those confidence rankings. So if we had looked at, in this paper specifically, when we did our analysis of the depletion mapping, had we looked at the mud gas data, we probably could have incorporated that to help make some of our decisions earlier, and even improve what our outcome was, our success rate, just using that context.
So speaking of the mud gas data, I know that the analysis had a proprietary process to eliminate noise.
Mm-hmm.
What can you tell us about how to differentiate that noise from something meaningful?
Yeah, so good question, because like anyone who's ever looked at mud gas data, and we get it on most of the wells, right? We see a lot of wells, and most wells have mud gas data, though I would challenge that very few people are actually looking at it, right? Even though they have it. And one of the reasons is that if you just look at the raw data, it is noisy as heck. I mean, it goes all over the. And the reason is because that is constantly changing depending on what's happening during the drilling process. In fact, one of the easiest things you can do is just look at the mud gas data from the beginning of a drilling stand to the end of a drilling stand, right? And that's whatever that is, 60 feet, let's say 60 feet. And you'll see this consistent trend going over that 60 feet. You need to account for that. And there's just a lot of other stuff that happens during there. But that's one of those we actually like to look at the ratios of the different gas, because even though the volume of gas that comes in through the sensor might change through all these stands, the ratios should stay more or less the same, right? So that's one simple thing you can do, is looking at the ratios of the different gases, as well as what the magnitudes are. But of course, that just takes a little bit more filtering, smoothing, and all that sort of stuff.
Thanks for
I will also say, excuse me, I will also say that in this paper specifically, we had a really good relationship between mud gas and everything else that was going on. That is definitely not the norm. Vast majority of the work we look at, sometimes you can see indications in that mud data, Many times you can't. A lot of it really depends on how they're drilling that well, and how they're measuring the mud gas, drilling processes, mud weights, mud rates, all of that plays into how useful that data is. So it's definitely not always useful, but often it is.
Thanks for that clarification. I was thinking a lot about seeing seeing areas of depletion and seeing the types of fractures and thinking about the correlations as well. So from what you've worked with with other clients, have you seen that correlation between spacing between primary and infill well and even geology versus how many fractures or for the infill well are depleted?
Yeah, absolutely. So, quite often, the majority of the time, we usually work on pads of wells, right? Pads of infills. So the first thing that you're typically going to see is that the number of fractures that you pass through are going to decrease as you move further and further away from the parent well. And of course, the magnitude also tends to decrease as you move further and further away. So there's definitely a relationship there, and some customers are using that to help understand sort of what their optimal spacing is. But another interesting thing is that when you're looking at our data is trying to understand where the well is stratigraphically, right? Because as you're going through different stratigraphic layers, we also need to understand that some of those layers are going to be more permeable than others, right? So if all of a sudden your wellbore dips into a very tight layer, low permeability, et cetera, we can't expect to see any depletion in that area, because even though a frac might go through it, there's not going to be any depletion associated with that frac. So every once in a while, we will see this, this happens often on wine racked wells, right? We're not, some in upper layers, some in lower layers. And you're going to see the same fracture sometimes through those different wine rack layers. But in some, you might see a large depletion when you're in the lower. When you get into the upper portion, it's much smaller. It stays very close to the fracture. You get down into the lower area, it's spread out, more depletion, et cetera. So one of the things we're actually looking at now is, can we correlate the depletion signature to the perm of the rock as well? And that should be possible just using sort of a standard Darcy equation, right? Sort of understanding how far you're going away, knowing what that drawdown is, knowing what the reservoir pressure is, and sort of building that curve to sort of understand what the perm is. So that's something that we're actually looking into right now.
Awesome. I'm looking forward to hearing that in a future paper, perhaps. So hopefully the client will let you publish that.
Yeah, that's always one of the problems we have, is getting permission to publish a lot of this stuff. But as I said, we were very lucky to be able to publish this, even though it was under the condition of anonymity.
Yeah, so. I'm sure. And I can't let you go without asking this question, because it's something that we touched a little bit on earlier in this podcast, but what are some of the completion implications of this work? I mean, just because we see depleted fractures, is that going to be enough for completion or for companies to switch to engineered completions?
Yeah, so, I think one of the things we need to probably discuss is what exactly is an engineered completion, right? Because I think people use that term differently, right? In my opinion, an engineered completion is just adapting your completion to the wellbore that's been given. It doesn't necessarily mean putting clusters in like rock, moving clusters around, or doing all that, but it can include that, of course. But really, when I say engineered completion, when I'm talking engineered completion, I'm thinking it's that, can you adapt what you're doing on your completion to the well that's been given to you? So in my opinion, the answer should be yes, you should be able to make some changes. So what a lot of our clients are doing when they get this data is designing the completion in such a way that they don't put any clusters directly on one of these pre-existing depleted fractures, right? A lot of different ways to do it. You can shift your clusters to avoid it. We have other clients that all they're doing is they're using their standard geometric design, and they're just omitting putting a cluster right at those pre-existing fractures. And that's really the best thing. The best thing you can do is just making sure you don't have any clusters directly on it. And what our clients have been seeing by doing that is significantly less damage to the offsetting parent well, right? So essentially by avoiding these fractures, usually all they're going to do is drop out, less than typically 1% of the total clusters that they're pumping within their well. They'll drop out less than 1%, maybe a handful of them. And as a result, they're seeing significantly less damage to their parent well. And at this point, we don't really have any clients that have gone to us and said, well, we're seeing a huge improvement in production in our child wells. Reason is because really they're not seeing much of an effect on their child wells, right? But they're definitely seeing that they're protecting their parent wells, right? And that's something that is really exciting a lot of people. And they're saying that they're seeing much better improvement in production after they bring that well back online. They're not having to do cleanouts anymore. And that right there is where their value comes in.
Awesome. Now, I think the parent protection is definitely something to consider in the primary infill well situation. I did a huge internal study on parent well recovery and what are some of the key drivers for those parent well recoveries, and definitely a modification and completions was one of those key drivers. So
yeah, and I just had a conversation with one of our clients just yesterday, and one of the things they were talking about is one of their plans for avoiding these parent-child interactions was to move their child wells further away from the parent well, right? And you need to understand that that's a huge potential, lost EUR in there, right? I mean, how much reservoir could you potentially be leaving behind by increasing that spacing? We know you need to protect that well, but so a little bit more of a targeted approach is sort of what we're offering, and saying, no, don't move it further away, but just make sure that you're focusing on the area that's not already produced, right? And potentially avoid some of those interactions from happening. And as I said, people are having some pretty good success doing it.
Awesome. Well, Kevin, it was a joy to have you on the podcast and let me pepper you with questions. And as I mentioned, I had a lot more questions than what I had before, but for the sake of our viewers and listeners' attention spans, I wanted to